Axial loaded members are those structural elements having straight longitudinal axes and carrying only axial forces. Axial forces is either tensile or compressive. That is to say that a member is either in tension or is in compression. If a member is in tension, it is being pulled apart and will naturally elongate as a result. If a member is in compression, it is being squished or pushed together and will naturally shorten as a result of the load. Stresses and displacements will occur in a member when loaded and must be calculated for design or analysis. So you have to ask yourself, what is the difference between analysis and design? Analysis is the determination or calculation of such quantities as stresses, strains, displacements, when we have known dimensions of materials. Design, on the other hand, is a more difficult task, and it is the determination of the required geometric configurations or characteristics, such as the materials, in order to fulfill all the prescribed functions that the engineer needs. Design and analysis are absolutely interrelated, but they are different. Optimization, as an aspect of design, is the tweaking or refinement to achieve the best design. Best could be described as least cost, lightest, strongest. There are a number of things that might go into being the best. So let's talk about internal forces for a second. We have seen in statics that we must have equilibrium for the whole or any part of the structure, and thus we know that external forces must be transmitted via the structure and are resisted by the internal forces. If I cut this simple rod in half, using the method of sections, we can see that the force applied at one end must be resisted by an equivalent internal force that is analogous to the external loads being transmitted by the structure. It is worth noting that we will adopt a sign convention for axial forces. Tensile forces will be noted as positive, while compressive forces will be noted as negative. Now, despite having just told you that internal forces are established to resist the applied loads, the truth is that they don't really. What manifests itself in a member is stress. So let's look at this area. That P is actually the numerical sum of the stress, shown as sigma in this diagram, across the entire area, which adds up to an equivalent internal load, P. Our first fundamental equation is given as P is equal to the stress times the area, and reflects this relationship between stress and load. Well, you're not required to memorize formulas in this course. This is a perfect example of a relationship that you just need to understand and know if you are to explore more complex issues. One note, this formula reflects, in the case shown, the average stress, where we are close to the point of load application or have other geometric discontinuities near where we are examining. It is very likely that there will be a higher and lower stresses across the cross-section. This concept that I'm talking about is St. Venant's principle. For our purposes in this course, we will be primarily looking at average stresses. Stresses, in effect, exist at a point, but we will be looking at the average stress across the cross-section. So, in our review of statics, we talked about units. We will be using SI units, and thus the load will be measured in newtons or kilonewtons, and stress will be measured in pascals or megapascals. We will, of course, insist on equations being completed in compatible units. Because civil engineer materials are typically strong, their material strengths are usually referred to in megapascals, which makes newtons and millimeters desirable because they go together to make a megapascal. That said, we often have larger loads and longer span lengths, so we often will start off in kilonewtons and meters, but need to convert to newtons and millimeters once we are looking at the cross-section and the stress. So the concept of stress. It is important to understand stress as it is related to the strength of the material, as compared to the load, which is more related to the strength of the structure. Let's look at two rods, a slender one and a bigger one. Cross-sectional areas are shown, the slender one with a 1 millimeter squared and the larger one with 100 millimeters squared. Each carries a load, in this case, of 100 newtons and 1,000 newtons respectively. For us to understand which one is closer to failing, we must look at the stress in the rod rather than simply the load. When we calculate it out, we see that the more slender rod has a stress 10 times that of the larger rod, while the larger rod carries a load 10 times that of the slender rod. The slender rod has a stress 10 times that of the larger rod because its cross-sectional area is so much smaller. Stress is the major factor for materials capacity. So let's talk about strain. Here we have a rod. If we hang a weight, P, on a rod, we can expect it to elongate. We observe this elongation and denote it as the deflection delta. How far it elongates is related to the load applied and the length of the rod. Thus we define a term strain, which is the intensity of the displacement. For a simple problem, we can determine the strain by dividing the displacement by the original length of the rod. Like stresses, strains exist at a point. So let's talk about a few of the limiting assumptions that we're going to apply when it comes to this introductory course on mechanics of materials. As it pertains to normal stresses, we're going to be talking about a prismatic bar, or a bar that is regular and does not have discontinuities in it. That being said, although we may introduce the odd discontinuity, we will be looking at the average stresses that exist away from the specific area of the discontinuity itself. It will be both loaded at the centroid of the cross-section and perpendicular to the cross-section, and thus we get a uniaxially loaded bar. And it will result in a uniform stress across the cross-section. Again, as I pointed out before, really this is the average stress, as we know that there will be some variation depending on discontinuities in and around the cross-section itself. For the strains, we see similar assumptions.